Hey Josh, how's it going? Good, tired, end of the week, excited for the weekend, the usual emotions on a Thursday afternoon. Yep, it's a big one. Yeah, definitely let me know if you're having trouble with it. That's good. Yeah, it is very long. I think that's the most challenging thing is that it takes so long to do. That's good. Yeah, 2 weeks from today. So not next week, the week after that. Next Thursday we have off anyway. So next Thursday is we don't have class next Thursday. Yeah, it'll be in person. Mhm. Mhm.
Are we gonna have a final for the final or just that?
Just the project. Yeah, yeah. No, there's no final exam.
Same as it's here or?
Same as here. Yeah. 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 So on Tuesday, we're going to be doing activity. What is it? I think it's 5 for this class. And so that's going to be on dynamics. And so, yeah, we're only going to do it for just a little bit because honestly, anything more, we'd have to go a lot deeper, which is, really difficult to do in such a short amount of time. But I at least want to show you how you can set things up and just enough just to get you started. But yeah, dynamics is hard. Yeah, it's hard in general, but in finite elements, it's hard. It's hard for other reasons too. Yeah.
Hey, Dr. Tran.
Hey, Steven, how's it going?
It is going. Quick question for our final project. When I do, or I was planning on at the moment doing one of the fins for the rocket we're doing, and drawing up some basic geometry or whatever for it in ANSYS to analyze, or in SOLIDWORKS to analyze and importing it over. We're only doing like a static structural type final type thing for it?
I'm not limiting you to it. And so I've had people in the past do like thermal, they did fluids on their final project. I mean, the stuff we're going over in the class is going to focus mostly on structural. I think we might have time for like a couple workshops at the end after Thanksgiving for like thermal and fluids, but the vast majority of the content of the class is for structural stuff. So I'm not going to stop you to doing thermal or whatever you want, but there's going to be a lot less support.
Yeah, there was just a specific condition I was going to try to replicate, but I think it's called like the fin flutter, and fin flutter is kind of a wicked a wicked thing to deal with when you're dealing with high speeds or whatever.
Yeah.
But I'm not too confident about analyzing it from that standpoint, because it would have been nice to like calculate out with the shear stress that it would take on. But I just kind of wanted your opinion of like bite off more than I can chew, or
I'm familiar with that problem. It's I think the true way to do it would be like a fluid structure interaction, like an interaction between like a flowing fluid past an object and it responding to it. That's really hard to do.
Okay.
And so I think
more than I can chew right now.
Yes, I mean, if you want to do a true flutter simulation, it would be really hard. But there's ways we can go around it too, and so we can talk about it offline. I think I think once we do activity 6, I think that might give you some ideas on how you can tackle it. So activity 6, we're doing modal and vibration analysis basically in ANSYS, and that's what we're going to do. I think first thing after we come back from Thanksgiving. Yeah.
Sounds good. Thanks.
Yep. Okay, it's 5:30, so let's go ahead and get started. Good evening, everyone. How's everyone doing today? Good. Yeah, week 11. I'm sure everyone's really busy. So, just as always, I always appreciate you guys coming to lecture. Right? First thing I want to say before I forget, next Thursday is a holiday. And so some people asked me about that after class on Tuesday. And so next Thursday is Veterans Day. So we're not going to have any class. And so next week, we just have one class session, which will be on Tuesday. And so Tuesday, we're going to be doing our next ANSYS activity. And then Thursday, we have no class because it's a holiday. Okay. And so I wanted to make sure I mention that before I forget. And then I'll send an email to confirm that as well. Okay. All right. And so the plan for today is we're going to do, a couple things today. And so first thing you might have noticed earlier today is that I posted the specifications and the rubric for the final project. And so I want to talk about that today first. Okay. Because it's, I really want to get this to you guys because it's, I want to make sure you have enough time to work on it. Okay. And then after that, we're going to have a relatively short lecture to kind of set the stage for dynamic simulations in FEA. Okay. And so the subject for the ANSYS activity on Tuesday is we're going to learn how to simulate dynamics in ANSYS. Okay. And in fact, so what we're going to be simulating on Tuesday is a car crash. And so we're going to be taking a car, or at least just the chassis of a car, and then just ramming that into a concrete wall. And so, today, we're going to do just the setup for it, just to, make sure that we kind of understand just the basics of the theory for dynamics. And then Tuesday, we'll put it in action into ANSYS. Okay. And so in terms of, I think, I guess, wow factor, the car crash activity is always a crowd pleaser. So, hope you guys enjoy that. Okay. All right. And so another question I got before the class is if there's going to be a final exam for this class. And so there's no final exam. And so the only final thing that I want you guys to do for this class is the final project. Okay. Personally, I've never liked it when I got, in the same class, I would get a final exam and a final project, because I feel like I could never really focus on both. And so, especially for this class where, the ANSYS is a big part of, what I want you guys to take away, I want you to focus just on that final project. And so, there's no final exam. The only exam we're having in this class is the midterm exam, which is 2 weeks from today. Okay. All right. And so I think that's all my announcements. And so, before we get into the final project specification, are there any questions I can answer? Homework is due next Friday. Yeah. 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 But I mean, of course, you're free to turn it in earlier if you want to enjoy your day off too. But I extended the deadline to Friday. Just to give you a couple more days. Okay, all right. So let's begin talking about the final project. Okay, so the final project is really not all that different from what you did on the midterm project, right? And so, I haven't looked at your midterm projects yet. I actually just finished grading my graduate students' midterm projects, but your guys I'll be probably grading all day tomorrow. Okay, but the final project is not that different. And so the biggest difference I would say with the final project compared to the midterm one is that for the final project, you get to choose, what your geometry is going to be, okay? So for the midterm project, I gave you a choice of 3 geometries, but the final project, I'm gonna let you choose your own, okay? And I think, if you kind of know the history of this class a little bit, traditionally this class is taught in the spring, but I asked the department chair if I could teach this in the fall, because I know there's a lot of you that are in senior design, a lot of you that are working on the legacy projects, right? And a lot of you guys, a lot of those students in the past would choose to do their senior design and their legacy projects for the final project for this class. But unfortunately, I always felt bad because I think a lot of times those students get really interesting results from their finite elements, but it was always too late. Like they can never really apply that to their senior design or to Baja or to Titan Arrow or Rocket or anything like that. Okay. And so I think this is going to be a really interesting semester because I think this is coming at the perfect time where you can run a finite element simulation on the on your senior design project or whatever, and actually get a chance to implement that before you actually start building stuff next semester. Okay. And so I'm from that perspective I'm really excited. Okay. All right. But besides being able to choose your own project, I think at this point you guys really understand how to conduct a finite element simulation, right? So you have to get the geometry, you have to choose the materials, do the meshing, boundary conditions, and all that. Okay, so I'm not gonna spend that much time talking about those aspects, because you guys just did it for the midterm project. But I did want you I did want to let you know that you can choose your own geometry here. Okay, and so. But you aren't limited to just your senior design project or any of the school projects as well. And so, I'd say maybe about half the students do that, but then the other half maybe do just a project that's just personally interesting to them, right? And so last year I had a student that did a simulation on a lemon squeezer actually. So that was kind of really cool. I've also had students that took like historical structures, like maybe like the Golden Gate Bridge, and simulated a part of that in ANSYS. And so, I thought that was really cool too. Okay, so it's really up to you. And so, your imagination and the CAD is really your only limitation for the final project. Okay. All right. So any questions on this so far? Okay.
Is there a set number of constraints or loadings that you at least want?
There's not, and so I'll leave that up to you. I'll leave that up to you guys because I think the amount of constraints and loadings I think is going to be I think it's different than the midterm project where I can control that a little bit more. This one, because it's so free form, it can be almost anything, and so I'll let you guys kind of decide on a lot of those things. Okay, and before I forget too, so and actually I forgot to move this to the front. I am going to allow you guys to work in teams for this project, okay? Because I know a lot of you are in this class, maybe together with other people in your on your project or other people in your senior design group. And it's not really fair if one person gets to do the senior design project and everyone else has to do something else. And so I am going to allow you to work in teams. I would prefer the teams to be limited to just 2 people max. But I am open. So if you have 3 people in here from like Baja or something like that, I don't want one person to be left out in the cold. And so, 3 of you can work on the same project, but we'll have to discuss about, what we can do with those 3 people to make it more appropriate, a more appropriate simulation to do. Okay. All right. So let's talk about the requirements in general. Okay. Okay. And so the first requirement here is the project objective. Okay. And so this is the same as your midterm project, but I think for this one, it's going to be even more important because since you guys are choosing your own subject for the project, you really have to think about what do you want to get out of this finite element simulation. Okay. And this is the part that I'm really excited about because, I think a lot of you are kind of at the point in the year when, you're maybe just about to start fabricating, or maybe you're thinking about redesigning something for your senior design or other stuff. And so I think, these objectives, I think are gonna be really, really cool because, a lot of times I would get objectives for senior design. It's like, it would be really cool if we could do this, but then it was too late to actually try it because the year was already over. And so, really think about your objective. Okay. And so, think about, what can you get out of a finite element simulation that you wouldn't be able to get otherwise. Okay. And how would you be able to use that information to actually influence your design? Okay. And so, I really want you guys to give this a good amount of thought. And, I want you to have a really decently formed idea by the time you submit your proposal too. Okay. All right. Background and significance. Okay. And so you also need to describe some background knowledge about your subject. Okay. And so, this is also going to be really important because you guys are choosing your own subject. Okay. And so you have to basically motivate why it's important to, for this part to even exist in the first place, right? And what are some of the most important things that you can get out of it? Okay. Maybe you can talk about maybe some of the historical background that led to the development of this technology, and what are some other kind of bigger questions that you can answer about this part. Okay. All right. Next is what I call the simplified model. Okay. And so this is, I think, the other big new part of this project is that I want you to create a simplified model for your subject, which you can use to check your finite element calculations against. Okay. And so, probably after Thanksgiving, we'll be going over a topic called verification and validation. Okay. And so we'll talk about there that, even though finite elements is a really powerful tool, finite elements can get things wrong as well. And in fact, it does that a lot. Okay. And so a big part of using finite elements, as an expert, is you have to be able to check your results. Okay. And so a lot of times people check their results against, maybe they just solve an equation, right? And so maybe they simplify your geometry into a really, just a thin beam or something like that. And then they solve some of the equations that you learned in the class just to make sure that you're getting answers in the right ballpark. Okay. And so your simplified model, I'm leaving this very vague because it can be almost anything. Okay. But I want you to basically solve your finite element simulation in a different way that's not finite elements, so that you can check your results. Okay. And so I think, for this project, this is the part where I get the most questions on. And so, definitely once you get to this part, don't be afraid to ask questions. I think, a simplified model will work kind of differently for everybody. Okay. But we'll talk about that a lot more once we get to V and V after after Thanksgiving. Okay. All right. So the next aspect is the finite element modeling methodology. Okay. And so these are all the material properties, meshing, boundary conditions. You just got done doing that for the midterm project, and so this should be, you guys have already done practice on this, and so I kind of lumped that all into one section here. Okay. And so I'm not going to talk about that much anymore. The only addition that you're going to have to do for this project compared to the midterm project is I want everyone to do a mesh convergence test as well. Okay. And so this was an optional activity, an optional problem in activity 4, I believe. But again, this is something we'll talk about after Thanksgiving once we talk about verification and validation. Okay. All right. Then you're going to show your ANSYS results. And so that's, pretty standard. Okay. Then you're going to do a comparison between your ANSYS results and your simplified model. Okay. And this is basically where you're going to check the work of your ANSYS simulation. Okay. And then you're going to have your conclusions. Okay. All right. And so you can see that there's some additional parts compared to the midterm project, but I think you guys have already done most of the most of the hard parts already. Okay. So the final project is just going to be kind of applying the same process that you did, but just to a subject of your choice. Okay. Any questions on any of this so far? Okay. Oh, question? The structure thermal, no fluid, but that's it. if you want to do CFD, you can do it by all means. You know, I've you know, not that many people. I think maybe like 2 or 3 people over the last 3 years done CFD. And so it's possible. It definitely is. You know, and I'm not going to stop you. It's just CFD it is a lot more difficult to set up. You know, I'll say that. I'm willing to work with you individually, you know, if you want to do CFD. But you know, it's a lot of it's going to be on your end too. Yeah. All right, so let's talk deliverables. And so there are going to be 2 main deliverables for the final project that you have to turn into me. Okay. And so the first thing that you have to turn in is a proposal. Okay. And so this is kind of a necessary part because, you know, because everyone's going to be doing something different for this project. You know, I want to at least have an idea of what you're trying to accomplish, you know, before you really start to set off on all of the really hard work. Okay. Because, you know, what tends to happen is that, you know, and I think there's a big disconnect because I think when the students typically see this, they think like, oh, I need to make a project hard enough or complex enough for the project to satisfy this proposal. Usually the problem is the opposite for most people. So usually the problem is that, you know, you guys have really great imaginations, you have really good engineering application that you want to do, but given the constraints of the class, a lot of times what you want to do just isn't possible within the constraints of the class. And so most of the time, you know, when people submit their proposals, I tell them to kind of tone it down a little bit. And so I said, you know, maybe let's do something simpler, just so that you can finish in time. Okay. But, you know, I think this part's important because, you know, because whenever you have kind of a free subject kind of project like this, there's a lot of variation in what people are trying to accomplish. So I want to take this opportunity to kind of rein people in, okay, just to make sure that every project is feasible, you know, within the confines of the class, okay. And so that's going to be due Sunday, November 14th, which is next Sunday. And so you have you have about a week and a half to think this up, okay. And so I'm going to give you points for this, and so, you know, I don't want you to submit this for nothing. And so I'm going to grade that just purely on completion, okay. And so, you know, if you submit a proposal, you know, I'll give you the points and I'll give you feedback on the proposal on, you know, on what you're going to do, okay. And so I want to make sure I get that feedback to you before Thanksgiving. And so, you know, if you turn in by the 14th, that gives me, you know, a couple days, you know, to give people feedback, just that you can really start working on it, you know, before the Thanksgiving break, okay. And so the other deliverable for the project is the final report. And so this is kind of the same as our midterm project, okay? And the due date for this is going to be Monday, December 20th, okay? And so that gives you, you know, a little bit over a month after the proposal is due to work on the project, okay? And unfortunately, you know, if you're keeping track of when this date is, this is the Monday after finals week, okay? It's also 5 days before Christmas. And so this due date here is totally rigid, and so I can't push this back under any circumstance because this is already kind of after what, you know, the department recommends for due dates. But I wanted to give you that extra weekend because I know, you know, finals week can always be really crazy, and so, you know, I wanted to give you that extra weekend and one extra day on Monday to work on this project, maybe write it up at the end, okay? But just so that I can finish grading and just so I can see my family for Christmas, you know, I can't push this back anymore because, you know, I really need to start grading on, you know, on the day after that, just so I can finish everything because I have your guys' class and I have 3 other classes I need to grade final projects for. So, so that date is set. You know, I can't change that anymore. Okay. All right, and so just a summary, and there's a typo here that should be a 9. But there's a project proposal that's due on Sunday, November 14th. And so you'll get 10% points just automatically just by turning in that proposal, okay? And the final report will be, there should be a 9 right here. And so a 90% of your grade, okay? All right, any questions on this? Okay. All right, and so here I have the components or the different sections of the final project or the final report. And so, you know, you can go over this, you know, on your own. I'll also post a template just like I did from the midterm project, which has all of these sections. And so, you know, you can just follow the template for that. Okay. Teams, you know, just like I mentioned, you can work together in a team. But, you know, I would prefer to limit it to 2, you know, maybe 3 at most. Okay. And just be aware that, you know, if you are going to work on a team, then I am going to expect more from the project than, you know, if you were doing it by yourself. Okay. So maybe that's, additional loading situations, maybe that's additional aspects to your report. It's going to be on kind of a team by team basis. And so, this is also going to be part of the feedback that they give you for the proposal as well. Okay. And if you're going to be working on a team, you only have to submit one set of deliverables. And so I don't need a proposal from everyone, and I don't need a final report from everyone. I just need one person on your team to submit this, and then I'll give the credit to everyone on the team. Okay.
For the team scenario, should we inform you ahead of time, or should we inform you with the proposal about the team?
You can inform me on the proposal, but if you want to talk to me before the proposal about it, then you can definitely do that as well.
Okay.
Yeah. Mm-hmm. Yeah, but I only need to know by the time of the proposal. Yeah. So if you already know kind of who you want to work with, and you kind of have a project set, then you can just tell me on the proposal, and that's fine. Yeah. Okay. All right. So some final remarks, and so I hope that this project is going to be it's going to be a lot of work, obviously, but I hope that it's also going to be fun, but I also hope that it's going to be useful for you guys too. Okay. And again, this is the first time I'm doing this project in the fall, and so I'm really looking forward to to seeing what you guys are going to do with the finite elements, and hopefully those results can lead to something useful for your projects as well. Okay. And so I talk to some of the senior design faculty, on a semi-regular basis. I get lunch with Dr. Lee every week, and a lot of times, like, he asked me if I can help with some of the finite elements for senior design. And so I hope this is kind of killing two birds with one stone, where I get a good chunk of you senior design students, and then you can use finite elements, and you can use that as part of your senior design project. And so I know Dr. Lee's in big support of this, and I know a lot of the other faculty are as well. Yeah, question.
Senior design. I think we have an activity in 2 weeks in which we have to analyze.
Uh-huh.
And he will prefer FEA.
Okay, excellent, great, yeah. So I know he's been trying to incorporate FEA into his class, and so yeah, he said quite a few of his students are in this class, and so I think this works. This is a win-win for everybody. Yeah. Okay. And another thing I want to mention too is that I know probably a lot of you guys probably at this point you're looking for jobs. Save this final project and save your midterm project too, right? And so when I was in your guys' shoes, I saved a lot of the projects that I did for my classes, and I brought them to my interviews, right? Or I submitted them as part of my application as like supplementary materials or auxiliary materials. And a lot of times, the interviewers, they asked me about it, and I was able to talk about, this is what I learned in the class. And so that's another aspect that I wanted to work into this project. I wanted to make this final report be something that you can present as saying that, hey, I'm an expert at finite elements. Like, here's the report that I did. Here's the receipts, right? Because I think it's one thing for people to say that I took a class in finite elements, or I'm proficient in the software. Because I'm guilty of this too. And so a lot of times I'll use a software once and I say, hey, I'm going to put that on my resume now, right? And so I use star CCM once. I'm an expert. I'm going to put that on my resume. And so the unfortunate thing is that recruiters know this, and so recruiters know that if you put a large list of software on your resume, that they ask the question like, do they really know what they're doing in this software? And so to really kind of separate yourself from those people that maybe they watched like a 15-minute YouTube video on ANSYS and they put that on their resume. This is how you're going to separate yourself from all those YouTube experts out there. Okay. And so this is the receipts. And so, keep this report, submit it to recruiters, and, and I guarantee you a lot of them is going to be impressed. And so every year I have at least, 2 or 3 students tell me that they took the final project from this class, they showed it to a recruiter, they showed it to like a hiring manager, and it helped them get a job because it really showed what they could do with ANSYS. And, it's always impressive. Okay. All right, and so that's the final project, and so the deadline for the proposal is fairly looming, and so it's next Sunday. So make sure you're thinking about it, and you send something to me by that. Okay. All right. Any final questions on the final project specifications?
The deadline for the proposal is Sunday. Is there ever a situation where you decline a proposal and ask us to think of something else?
I've never done it. At least not for the 3 times I've taught this class before. I've definitely asked people to kind of maybe let's take it in a different direction, but I've never flat out said no, redo this thing. But I've had times where I said I think this is an interesting idea, but maybe let's simulate this situation, or maybe let's take it in this direction. And so yeah, there's you know, as long as you put some decent thought into it, you know, we can work with almost anything that you come up with.
Okay, cool.
Okay, all right, and so that's the final project, right? And so, you know, throughout this whole process, you know, don't be afraid to reach out, you know, and ask questions. I think that's how, you know, that's how these projects are usually done. Okay, so let me stop sharing here and come back to my iPad. Oops. Okay, and so the subject for today's lecture is going to be dynamic simulations in ANSYS. Okay. All right, so here's the learning objectives, and so I know this is kind of flashing on the screen really quickly, but you know, I did want to make sure we get to the meat of the lecture quickly. Okay. All right, so let's say dynamics. Dynamic simulations in ANSYS. Okay. Okay. So before we really start, you know, I do want to give a disclaimer here that you know, we're going over the basics of the basics of the basics. Okay. So the whole theory behind doing dynamics just with any computational method, not only just finite elements, that is really deep. And so, you know, we're not going to have time to really go through all of the issues that can show up in all the theory. Okay. Okay. You know, because, you know, once you start you know, start to simulate time-dependent phenomena, which is what dynamics is, then, you know, a whole crop of issues that can show up. And so, you know, ANSYS, I'd say ANSYS does a pretty good job of I wouldn't say hiding the issues, but making it not an issue for the typical user. But even that, but because of that, you know, there's only so much you can do with such a surface level understanding. But even with the surface level understanding, you know, I think it's enough there to at least get you started with it, and at least get you, you know, to the point where you can run some basic dynamic simulations. Okay. And so if you want to learn more about how to run dynamics simulations in, you know, maybe not in FEA, but just in general with computers, we have a class for it. Okay. Okay. And that's EGGN 403. I might have mentioned this on Tuesday, actually. Okay. All right. And so the title of the class is like something numerical methods. Okay. And so if you want to learn more about, you know, how to simulate time-dependent phenomenon, that's the class to do it. Okay. And so in that class, you know, they use MATLAB, and so they don't use ANSYS for it. But, you know, a lot of those ideas, a lot of those concepts can be applied to FEA as well. Okay. And that's a class I hope to teach one day. If I ever get on the dean's good side, then that's a class I'll be able to teach maybe someday. Okay. Okay. And so another thing I want to say about dynamic simulations before we begin is that dynamic simulations are a lot more expensive than static ones. Okay. Okay. And so a big chunk of the activity on Tuesday is going to be, you know, just waiting for ANSYS to finish. Okay. And unfortunately, you know, there's really no way around that. And so, you know, it may not make for an exciting activity because you're not clicking stuff in ANSYS all the time, but it's just kind of a necessary evil when you're doing dynamic simulations. Okay. And let's kind of just talk about the reasons why. Okay? And so when you do a static simulation, right? Or even more generally, just a static, situation in general, right? So the word static, what that means is that it does not change with time. Okay. And so to capture this, or to to be able to visualize it, all you need is just one snapshot or one picture. Okay. Okay. I mean, granted, in ANSYS, we're doing like a 3D snapshot where you can kind of zoom around the zoom around your object, but it's just one still image in space, basically. Okay, or one still image in time. Excuse me. Okay. Okay. A dynamic simulation, on the other hand, or dynamic situation, changes with time. Okay. Okay. And so in order to capture all the information about a dynamic situation, you can't just do it in one snapshot. Okay. And what you need instead is a series of snapshots that you take in quick succession on each other. Okay. And what that makes is basically a video. Okay. Okay. Right. And if you think about just on your phone, right? And so when you take a picture, it takes up a certain amount of memory on your phone. But if you take a video, that usually takes up more memory, right? Because a video is always a series of snapshots stitched together. Okay. And so if you kind of keep that analogy in mind, right? So when you run a static simulation, you're running just really one simulation, right? And so you're simulating just one condition, right? And so you're applying your boundary conditions and you set everything up really carefully, and then you run it, and you just run it once and you get all your results. Okay. For a dynamic simulation, each snapshot or each frame in your video has to be a separate simulation. Okay. Okay. Right. And so in order to get just one dynamic simulation done, so let's say that you're going to simulate just 1 second worth of action, right? And so, let's say that you're using like we'll use video terms here. So let's say that you want to capture a video that's 30 frames per second. Okay. And so in order to capture that 1 second of information, you need to run 30 simulations in order to capture those 30 frames, right? Because in each frame of that video, the boundary conditions or the positions of the subject is going to change, right? And so each one is going to be a separate simulation, right? And so and this problem compounds even more. So maybe you want to get even more frames inside that second, right? And so this is going to be just naturally a lot more expensive because you need to run multiple simulations. At the very least, I would say dozens, but at the most, it can get up to a lot of the simulations I run, for my research can get up to like the tens of thousands, hundreds of thousands frames. And so, it can get expensive, right? And so, keeps on, and so just kind of keep that in mind when you're running dynamic simulations, that the cost is going to be a lot higher. Okay. All right. Any questions on this? Okay. All right.
I have a question.
Sure. Mm-hmm.
Does it involve solving like time-dependent partial differential equations? Kind of. Is it
It
like
does.
that?
It does, and that's the perfect segue, because that's exactly what I was going to talk about. Yep. And so what Jasmine was just mentioning is that when you have dynamic situations, your differential equation is actually going to change, right? Okay, because for static situations, in static situations, your differential equations are only a function of space. Okay. Okay, and so the variables that we use for space are just the Cartesian, just basically just the Cartesian coordinates, since we have x, y, and z. Okay, and so you're going to have differential equations that that are derivatives in terms of these. Okay, and so some terms that you might see are like maybe partial u, partial x squared, maybe partial u, partial y, things like this. Okay, right. But for dynamic simulations, you still have the spatial dependence. And so, we still have our dependence on X, Y, and Z, but we also have a new dependence on time, okay? Okay, and so we have X, Y, Z as usual, okay? But then we also have T there as well, okay? And the unique thing about these differential equations, and so, now you would have terms like maybe du dt, okay? Right? Or maybe dt dt, okay? Okay. What's unique about having time in your differential equations is that the methods that you use to solve it are actually different, okay? And so when you have spatial dependence, you're gonna basically discretize this, or you're gonna solve this using finite elements, okay? And so this is going to be the same as before. Okay. But time is a very unique thing, right? And so time, when you want to solve for time, computationally, you can't apply finite elements to it, or at least not in the traditional sense, okay? And so the way that the time variable is usually handled is with a certain class of methods called time marching or time integration. Okay. And so unfortunately, we won't be able to get into the specifics or the details of, what a time marching algorithm is or what a time integration algorithm is. Again, that's the subject of EGGN 403. But I can tell you, what are kind of the characteristics of this method, and more importantly, what is it that you as a user have to know about these in order to actually use it in practice. Okay. Okay. All right. And so I would say the two most important things that you need to specify in a time marching algorithm are the time step size. Okay. And so traditionally this has the symbol delta t. Okay. Sometimes you might see it as dt. Okay. For those people who don't like using equation editor on Microsoft Word, and so those people use dt. But I think delta t is the more traditional symbol for it. Okay. Okay. And the other thing that we have to specify is the number of time steps. Okay. Right. And so you'll at least set one of these indirectly when we do our activity on Tuesday. But I think it's important to know what they represent and what they can be, and what they're used for. Okay. All right. Any questions on this? Okay. All right. So let's start with the time step size. And so, let's go back to our video analogy, right? And so if we go back to our video analogy, right? A lot of times we rate the quality of the videos in terms of how many frames or the time, or how many frames that there are per second, right? Another way that we can say that is we rate the quality of the video based on how much time there is in between the frames, okay? And so the time step size is exactly this, okay? Okay. And so I think the best way to visualize this is with a number line. Okay. Right. Okay. And so this number line here represents time. So let's say that time is moving forward from left to right. Okay. And so let's say that we start our simulation and then we solve for the solution at time step n. Okay. Right. So maybe that's the initial frame in our simulation. Okay. And so when we move on to the next time step, okay, we're gonna run another simulation basically for time step n+1. Okay. And so what the time step basically tells us is how much time is going to elapse between simulation 1 and simulation 2. Okay. And so this distance right here, or say this amount of time, this is delta t. Okay. Right. And so delta t is a user specified parameter. Okay. So it's something that the user almost always has to specify. Okay. I say almost always because ANSYS actually has an auto time selector, and so actually a lot of times you don't even have to do that. But it's important. I think it's the single most important parameter in dynamic simulations. Okay. And so the intuition that you have for delta t, you can kind of match that up together with your intuition of the mesh size. Okay. And so if you have a smaller delta t, okay, and so let's say that you make delta t pretty small. Okay. And a small delta t, it depends on the situation, but I would say if you have your delta t less than 1 millisecond, okay, that's pretty small to me. Okay. Right. And so if you have the smaller your delta t is, the more expensive your simulation is going to be. Okay. Right, because if you can imagine that, maybe we want to simulate up to this point, and if we make delta t smaller, that means we're going to need to evaluate a lot more points, right? And so we're going to need to do all of these points on this line right here. Okay. And so because of that, it's going to naturally just drive up the cost of the simulation. Okay. Usually when we have to pay more computational cost in finite elements, usually we get something good out of it. Okay. And the thing that we get good here is naturally a more accurate, a more fluid simulation. Okay. Okay. And that's, almost always a good thing. Okay. One more nice perk that you get for a smaller delta t is that your simulation is going to be a lot more stable. Okay. And so what is stable mean? Okay. And so dynamic simulations have this unique, well, I should say it's not unique to dynamic simulations, but it's a lot more likely to occur in dynamic simulations where your simulation is just going to give you garbage in return. Okay. Okay. And so what I mean by garbage results is that, it'll tell you, let's say that maybe you're applying a dynamic simulation on a cantilever beam, right? And so let's say that you just have a time-dependent force being forced onto a beam, okay? If that simulation went unstable, the simulation might tell me that the deformation would be like, I don't know, 50 meters, right? And so if you have like a simple beam and you're getting a deformation of 50, when your beam is only like 10 centimeters long, that's something fucked up, right? So something went wrong. And so that's usually what I mean by an unstable solution. So you just get results that are just obviously not physically possible, okay? And sometimes it might even give you an error result, okay? And so sometimes you might see, and if you've taken a MATLAB class, this might give you nightmares again. Okay, and so you might get results that say not a number or NaN, okay? And so those are unstable results, okay? And so and I use this term all the time, and I have to actively stop myself. And so the informal term, so when you have an unstable solution, usually what people say informally is that your simulation blew up, right? And so it kind of blew up into a very large garbage result that was not not physical. Okay, I have to be careful using that though, because whenever I bring that up, someone always asks me, it's like, so is my computer going to blow up? Is my computer going to be okay? Your computer is going to be fine, and so it's nothing bad is going to happen to your computer. It's just that the solution values got so large that we say that they kind of blew up. But yeah, nothing bad is going to happen to your computer. You just get bad results. Okay. Something bad might happen to your computer afterwards if you get frustrated and kind of like bang on your computer, which I've done before. I haven't broken any keyboards yet, but I've gotten close. But this is something that can happen in dynamic simulations. Okay, but if you use a smaller time step size, you kind of reduce the likelihood of that happening. Okay. And so the smaller your time step size, the more likely your simulation is going to be stable. Okay. And so that's kind of one added issue that you have for dynamic simulations that you don't have for static simulations. Okay. Static simulations, I say on the most part, are very, very stable. But dynamic simulation can get away from you if you're not careful with the time step. Okay. And so, again, this is one thing where, we just don't really have time to dive into the theory of kind of why this happens. But just be aware that it happens. And if you do start getting garbage results from your dynamic simulation, try lowering the time step size and see if that helps. A lot of times that's kind of what helps you. That's kind of the cure-all for this stuff. Okay. All right. Any questions on this? Okay. All right. And so that's what happens when you have a smaller time step size. Let's talk very briefly when you have a larger one. Okay. And so when you have a larger time step size, you know, obviously your simulation is going to finish faster. Okay. Okay. Oops. Your simulation will finish faster at the cost of accuracy and at the cost of stability. Okay. Okay. All right. And so I think a fair question to ask is, you know, so let's say that you're running dynamic simulations for the first time, or maybe it's not your first time, maybe you're just using it for a new situation. How do you know, how do you know what to set for the time step size? Okay. Okay. And so unfortunately, you know, there's no kind of one rule fit all thing for time step size. It really is application dependent. Okay. But the advice that I can give you is that, you know, the time step size should be small enough such that you can reasonably capture the phenomenon that you're trying to capture. Okay. Okay. And so, you know, I'll give an example of what of the time step size that I usually do for my work. Okay. And so a lot of my research work involves simulating blood flow in the human body. Okay. And so, you know, most of the action that occurs in blood flow occurs over the course of about 1 second. Okay. And so 1 second is about the time it takes for the heart to beat once. Okay. And so your time step size should be able to capture basically everything that happens within a single heartbeat. Okay. And so for me, you know, what I want to make sure I do is that, you know, within that heartbeat, I capture, you know, every single little detail that the blood flow is doing. Okay. And so I usually, you know, the time step size that I usually start out with is 1 millisecond. Okay. Okay. And so with the time step size of 1 millisecond, this gives me about 1,000 frames per second. Right. And so I'm going to get 1,000 frames for 1,000 snapshots within a single heartbeat. Okay. Okay. And so that's usually, you know, and honestly, sometimes that's a little bit overkill, but you know, but that's okay. And so, you know, for my application, sometimes overkill is better than not. Okay. And so I'll give you an example where you might need to even go lower than this. Okay. And so let's say that you're simulating a combustion reaction inside a car engine. And so combustion reaction happens super quickly, right? And so your combustion is going to, you know, your fuel is going to meet your oxygen, it's going to ignite, and it's going to go and be done like, you know, in much less than a second. Okay. Okay. And so if you use a time step size of 1 millisecond, that might not be sufficient in this case, because you probably need to go a lot smaller than that. And I have to talk to Dr. Wang and ask him, how long does a typical combustion reaction takes place? But I just know that it's super fast. Okay? And so that's a situation where you would want to go lower for delta T. Okay. Right. But maybe you have a situation that doesn't take that long, and so maybe your situation, all the action is going to take place over the course of 10 seconds, right? And so maybe you're simulating a gear inside an engine, right? And so maybe to make one full revolution, maybe that takes 5-10 seconds. Okay. And so for those situations, you can use a larger time step size, just because things aren't going to change from 1 millisecond to the next all that quickly. Okay. And so it really just depends on what application that you're looking at. Okay. And so for the situation we're going to simulate on Tuesday, right? So we're going to be simulating a car crash, right? And so a car is basically going to hit a concrete wall, okay, and it's going to react to that crash. Okay. And so that car crash is something that's going to happen very, very quickly as well. Okay. Because we're going to simulate to the point when the car is basically right on top of the wall. Okay. And so basically, right when the simulation starts, the car is going to impact the wall, and it's going to start to crumble. Okay, and so that's another thing that's going to happen really quickly. And so we're going to set the time step size, pretty small for that one as well. Okay. All right. Any questions on this? Okay. All right. So that's time step size, and so I want to make sure I talk about that a lot, because I think that's the most important aspect of dynamics. Okay. The other thing that you have to set is the number, either the number of time steps or the ending time. Okay, and so they both kind of do the same thing. Okay. And so in addition to setting the the amount of time between frames, we have to basically tell us, we have to tell ANSYS, how long we're going to make this recording for, or for how long we're going to make the video. Okay. And so usually when you set your ending time, or you set your number of time steps, you set it such that you're going to simulate all the interesting phenomenon that you can. Okay. Okay. Right, and so if we go back to the heart flow example, right, and so I want to make sure that my ending time is at least 1 second, so that I capture the entire heart cycle, right? I think for the car crash, I think because it happened so quickly, I think the ending time for that's going to be like, I think almost like 200 milliseconds or something like that, or maybe even something less than that, because it happened so quickly. Okay, and so this is another thing that you have to set. Okay. All right. And so that's the time step size and numbers time steps. So I want to make sure I go over those, because that's going to be really important to set, no matter what kind of dynamics simulation you're using. Okay. And so for the last 15, 18 minutes of class, I want to talk about specifically what's available to you in ANSYS. Okay. And so in ANSYS, there's actually a couple different methods that you can use to perform dynamic simulations. And I think people get confused between the two. Okay. And so the two methods that are available, one is called transient structural. Okay. And the other one is called explicit dynamics. Okay. Right. And so they're two words that, or they're two analysis systems that at the end of the day, they both do the same thing. Okay. And so with both of these methods here, you can essentially accomplish the same thing. Okay. So both can perform a dynamic structural simulation. Okay. Right. And so, end of the day, you can actually choose either one, and it's going to work for most cases. Okay. Where they differ, the main way that they differ is in how they implement the time marching algorithm. Okay. Okay. And so because of this, because they have different implementations of the time integration, some situations will be better suited for transient structural, and some situations will be better suited for explicit dynamics. Okay. Okay. But even then, there's a lot of overlap, and so there will be some situations that maybe it works better for transient structural, but you can still do that situation in explicit dynamics too, and vice versa. Okay, it's just so that with one method or the other one, you might get a higher quality solution, or maybe even just a faster solution just in general. Okay. Okay. How much time? Okay. And so let me give you the use cases, for each one first, just so that we make sure that we cover that, and then I'll talk about what really makes the two different in terms of implementation. Okay. All right. Any questions on this? Okay. All right. So let's talk about the use cases. Okay. All right, so let's talk transient structural first. Okay. And so the way transient structural is implemented, it almost guarantees you that you have a stable solution. Okay. I say almost because it's still possible to break it, but it's really hard. Okay. And so this is true even if you use a relatively large time step. Okay. Okay. And so all that, we were talking about earlier about stability and, having to use a smaller time step to get stability. For transient structural, that's almost not an issue, okay? And so transient structural is great for situations where you want to have a larger time step, okay? Okay. All right, so as an example, let's say that we're performing a simulation of I don't know, maybe a door closing, okay? And let's say that, this door has one of those like stopper things that we have on the classroom here. And so it's going to take, maybe 5 seconds for the door to fully close. And so from all the way when it's open to all the way when it's closed, it's going to take 5 seconds. Okay. 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 And so, let's say that we use a fairly standard delta t here. So let's say that I want to simulate this phenomenon with a delta t of 0.001 seconds. And so this is 1 millisecond. Okay. And so if you do the math, right? And so with a time step size of 0.001, and I want to simulate, and my end time is 5 seconds, this means that we're going to have to run 5,000 simulations. Okay. And that's a ton. And so that's not a trivial amount. And so, if you try to run 5,000 ANSYS simulations on your computer, I'll see you next week or something, okay? Because that's going to take a long time, right? And so you don't want to do that, okay? And so if you want to simulate something like a door closing that takes place over 5 seconds, probably you're going to want to use a larger time step for this, okay? All right, and if you can kind of visualize, a door closing, from 1 millisecond to the next, nothing's really changing all that much, okay? And so for a situation like this, maybe we want to use this, a time step size of maybe like 0.1 seconds, okay? Okay. And so with the time step size of 0.1 seconds, right, that means we're going to run 10 simulations per second. And so this is only going to take us 50 simulations in order to get the job done. Okay. And so 50, still substantial, but 100 times better than 5,000. Okay. And so, maybe you can run the 50 simulations and go get a snack or something, or go to the bathroom, and then, maybe you come back and they'll be done. Okay. Right. But normally, the concern is, when you run such a large time step size like that, like 0.1 seconds, you might run into stability problems. But if you're using transient structural, then you don't have to worry about that. And so you can use a time step size of 0.1 seconds and not have to worry about stability at all. And and you'll be almost guaranteed to get yourself a good solution. Okay. And so that's the that's the kind of situation where you would want to use transient structural. Okay. And so usually for things that take place over a longer period of time, transient structural is usually better for this ones. Okay. The downside of using transient structural is that per simulation or per time step, each simulation is pretty expensive. Okay. Okay. because what's happening under the hood is that ANSYS is doing a lot of kind of extra calculations to basically give you that stability guarantee, okay? And so that makes each time step pretty expensive. And so you don't want to use transient structural when you have, a ton of time steps, because each time step you're going to be kind of paying a lot for it, okay? Right, and so that's transient structural, and so that's not the one that we're going to use on Tuesday, but I wanted to make you aware of it, in case you're interested in using it. Okay. And so when I mean expensive, when I say expensive, do I mean time consuming? Yeah. Mostly it's time consuming, but it's also taxing on your computer and on your memory as well. Yeah. Mm-hmm. So actually, for my own research, the method that I ended up using, it's a little bit of a hybrid between, what ANSYS calls transient structural and explicit dynamics, but it's a little bit closer to transient structural. And so, my simulations, they ended up being pretty expensive. And so most of the time I run those on supercomputers, where I can use 64, 96 processors for a single simulation. And so, when you're using a method like this, on a mesh that's, several million elements big, you need that extra computing power of that many processors. Yeah. All right, any questions on transient structural? Okay. All right, so let's talk about explicit dynamics. All right, and so with explicit dynamics, all of the weaknesses of transient structural, explicit dynamics covers that. And so on a per time step basis, explicit dynamics is a lot cheaper than transient structural. Okay. Okay. All right, and so what I mean by that is, the amount of time it takes for explicit dynamics to run 10 time steps is way faster than the time it takes transient structure to run 10 time steps, okay? And so this one can run time steps really, really quickly, okay? The downside to using explicit dynamics is that is instability, basically, okay? Okay, and so if you're not careful with the time step size in explicit dynamics, your simulation can go unstable, okay? And so when you use explicit dynamics, you're kind of limited in that you kind of have to use a small time step size, okay? Okay. And so what are situations where you want to use explicit dynamics? Okay. And so explicit dynamics works great in situations where you wanted to use a small time step size anyway. Okay. Okay. And so we've talked about, situations where you want to do this, okay? And so these are basically situations that happen really quickly anyway, okay? And so something like a car crash, right? Something like a combustion reaction. And so anyway, for those situations where, the phenomenon is going to happen really quickly, you're going to use a small time step size anyway. And so you might as well make it so that each time step that you run is going to be a lot cheaper, okay? And so those are good situations to use explicit dynamics for. Right? Right? And so that's the reason why we're going to use explicit dynamics for our activity on Tuesday, because a car crash is going to happen, almost in the blink of an eye. Okay. All right. Any questions on this? Okay. All right. So we have 2 minutes, and so it's kind of an awkward time because it's not enough time to really cover anything new. But I will give you the buzzwords. And so is anyone taking numerical methods right now, or is anyone taking it in the past? Yeah, usually not. It's a little bit of a niche, a little bit of a niche subject for mechanical engineering. I think it's more electrical engineers and computer engineering that take it. But if you do end up taking that class, the kind of the buzzwords that you can use that you'll hear. So you'll hear something called implicit. Okay. Implicit methods versus explicit methods. Okay. And so explicit, it's actually in the name here. So our explicit method here is explicit dynamics, but transient structural, that is your implicit method. Okay. And all implicit methods share that same property where, it's a lot more stable. It's very hard to get an implicit method to go unstable. But it is a lot more expensive because just because of the math and the equations involved. Okay. All right, and so if you do end up taking those classes, you'll hear those words, and this is how you can connect it to what we covered in this class. Okay. All right. Any final questions before we wrap it up for today?
So regarding this class, EGGN 403, I believe.
Yep.
Yeah. So I was just reading about it a little, and then it was just saying that. Are these kind of like equations that the solutions that you're guessing for them are just more like exponential, sine, cosine, instead of like polynomials, right? So we just basically kind of the same thing we solved in like 541, but then with these types of solutions, right?
Yeah. So it's so personally, I think the class is really cool, but you're going to be spending a lot of time solving like pretty basic math equations, but in math. And so eventually down the line, numerical methods leads to something like a finite element class. It just takes a lot of steps to get there. So, I think it's really cool, but actually a lot of the students that I tell to take it, they get mad at me afterwards because they said it was either really boring or they said it was not fun. So take that with a grain of salt. Okay. All right. So we're out of time for today. So thank you everyone for tuning in. And so Tuesday, we're going to have our next ANTIS activity. So look forward to that. And then Thursday's a day off. And so, Thursday, we're not going to have any lecture. All right. And so have a great weekend, everyone. Hope you guys enjoy the rest of your evening, and I will see you next week.
Thank you, Professor.
All righty. Enjoy your weekend. Thanks again.
Thanks, you too.
Thanks, Dr. Tran.
Thanks, Stephen.
Dr. Tran,
Oh, hey.
Another question, sorry.
Sure.
I have a question about the project. I'm just doing the global stiffness matrix.